Hi guys, so in this lecture video, we will be going over the synthesis of alkynes. So how do we make our alkynes? Unfortunately, there's actually a very limited way how we can make the alkynes. And we have seen already before that the alkyne consists of the two double bond in them, right? And we can see that already in order to make a double bond, we can do an elimination reaction on it. And now the alkyne has two double bond in them. So that basically means that we have to do 2 rounds of elimination reaction in order to make the alkynes. So that is basically the concept of making the alkynes. There have to be 2 rounds of elimination to make the alkyne. And there's not a whole lot of way of how that is possible. But one way that is possible is as follow. We can start from an alkyl dihalide. Now, an alkyl dihalide is basically when we have two halogens that are bonded, that are attached to a hydrocarbon chain. And here in this case right here, the dihalide have to be very specific in order for us to convert them into the alkyne. And in which that the two halides has to be connected to the same carbon or the two adjacent carbon. When the two halides are bonded to the same carbon, we call that a geminal dihalide. Or when the two halogen or the two adjacent carbon, then we call that the vicinal dihalides. So that are the types of alkyl dihalide that we need to have in order to make the alkyne. If the two halogens are now connecting on one on carbon 1 and then the other high halide on a different carbon, let's say carbon 3 or 4, then that would not be sufficient for us to make the dihalides or make the alkyne. So again, please remember that our dihalides has to either be geminal or vicinal in order for this to work. And once we have this dihalide ready, then we can know that this halide right here are good leaving group. So essentially, we can do elimination reaction on them. So we can do 2 successive elimination to produce the alkyne by using 2 equivalent of a strong base. And the base that we normally use for these purposes would be sodium amine or potassium hydroxide. Potassium hydroxide would work too, but the reaction rate would be slower compared to the sodium amine, because that is a much stronger base right there. And this is how the mechanism of this reaction would work. Let's say that we have a geminal dihalide. So when we treat this with a strong base, the strong base would do an E2 reaction, where we then come in and pick up this hydrogen right here. So this hydrogen right here is beta with respect to this leaving group. Okay, so again, it pick up the hydrogen on the beta carbon compared to where the leaving group would be. So here in this case, this hydrogen right here or this hydrogen on top, it does not matter which one. So one of it would then get picked up, and then the electron is then donated in, followed by kicking up this leaving group right here. And now we'll be able to convert this into this alkene. And this alkene right here has another leaving group on it that is connected to the vicinal carbon. So from there, we'll be able to do another elimination where we now use a base, and the base will come in and pick up the other beta hydrogen. And now the electron is donated in and now kick off this leaving group. And in the end, we now have our alkyne. So that's how alkynes are made from the geminal dihalide by using 2 successive elimination reaction. And similarly, if we were to have the vicinal dihalide, then the reaction would be very, very much the same. We would treat this with a strong base. And again, we'll be seeing 2 rounds of E2 reaction, where the base will then come in and pick up one of this beta hydrogen. So this is the beta hydrogen with respect to this leaving group. So this electron will then be donated in and now kicking off this leaving group right here. And so we will be able to basically make something very similar to what we have seen above here. And then on the second round, the base will now come in and pick up the other. So the base will come in and I'll pick up this hydrogen right here. This hydrogen is beta compared to this leaving group. And now the electron will be donated in and now kick off that leaving group. So in the end, we'll be able to make our alkyne as well. So that will be the way how we will be able to make our alkyne from the alkyl dihalide. And so here in this case right here, we have seen already that based on the example and the starting structure of the dihalide that we are making the internal alkyne right here. So both of these are internal alkyne. And we know this internal alkyne right here because they do not have hydrogen on them. Please keep in mind as follows. Depending on the structure of the dihalide, we may end up with a terminal alkyne. And whenever a terminal alkyne is being produced, then we need to have a water workup step in order to protonate the alkyne. For an example, let's say here we have these types of dihalide where there is a hydrogen right here, and this dihalide right here is staying on the terminal. It is on the end of a hydrocarbon chain. By taking this dihalide right here and treating with two equivalents of sodium amine, then we'll be able to convert this into a triple bond as well, the alkyne. So basically, this come in and pick up this hydrogen. And again, please remember this, that we can only pick up the hydrogen that is on the beta position compared to where the leaving group would be. So these two hydrogen right here are beta with respect to this two bromine leaving group. We cannot pick up this hydrogen right here. Okay, please remember that. And now that will come in and kick this off, and that does the same thing and kick this off, so we'll be able to make our triple bond. And note that in this case right here, we will still have this hydrogen on this alkyne. And this is basically what a terminal alkyne would be. And now that we recall, the terminal alkyne have this hydrogen right here that is acidic, right? So its pK right here is about 25. And if we would still have base in them, whether or not that we have two equivalent or even we have less than that, because we are producing something here in this case right here that is quite acidic. So therefore the base would then come in and pick up this proton right here. So toward the end of the reaction, we will basically end up with a deprotonated alkyne, or the alkali ions. And so the product right now is not neutral. In order to neutralize this product right here, we now have to do a water workup step. A water work step basically means that water is added. And when water is added, it provides the source of proton, where now this alkyne can come in and pick up the proton from water. And now converting this into the neutral form. So this is now our neutral alkyne. Okay. So therefore, please remember that if we were to be producing a terminal alkyne, then we need this water workup step. If we were to be using sodium hydroxide rather than sodium amine, then our product would not be sufficiently deprotonated, but then it would always good to do a water workup step, despite of which base that we want to use. So that is how we will be able to make our alkyne. And now there is now another reaction how to also make the alkyne. And here in this case right here, we are making an internal alkyne from a terminal alkyne. So synthesis of internal alkyne through alkylation reaction. This is how we can convert a terminal alkyne into an internal alkyne. And the reaction is as follows. First, we take our terminal alkyne that have this acidic hydrogen on it, and first we treat this with sodium amine in the presence of ammonia. So this, we know that this will be a strong base right here. And so this will be basically come in and deprotonate this and converting this into this alkyne product right here. And once we have this alkyne product right here, this carbon is now a good base and a good nucleophile. So if we were to now take this and react in this with an alkyl halide, then the alkyl halide, this carbon, there's a carbon here on this alkyl halide right here that is good electrophile. So this would be able to come in and attack this and kick off this leaving group, doing an SN2 reaction. So this is why that we have to be very careful about what types of alkyl halide that we added in here. So it will work with the primary alkyl halide or the secondary. But if we were to have a tertiary alkyl halide, then this would not work because the E2 reaction will be favored over the substitution, the SN2 reaction. And now we'll be able to add this R2 group to this carbon right here. So what we have successfully done now is converting a terminal alkyne into the internal alkyne. And now let's try some of this example right here. Predict the product of this reaction right here. So when we take this reactants, treating this with excess, so this XS right here stands for excess of sodium amine, followed by water workup step. What would then be the reaction? So here in this case right here, we do have a geminal dihalide, right? So this is a geminal dihalide because the two halogen are connected to the same carbon. And now, so here in this case right here, so this is our alpha carbon, and this is our beta carbon and our beta carbon. And we can see here in this case right here, we need to have two beta hydrogen in order to make the alkyne. And here in this case right here, we can see this carbon right here have three hydrogen on it. So that's basically more than enough hydrogen than what we would need. We will not be able to form the alkyne on this carbon right here because this carbon right here have no hydrogen on it. But the alkyne will be able to form right here between these two carbon, between this alpha and this beta carbon, where it actually have beta hydrogen on it. So here in the course of this reaction, then we will see we'll be able to form this triple bond. So that will be the product of this reaction right here. And so now initially after the first step, please note that this when we be after the product of the first step is when we still have this terminal alkyne right here with a hydrogen on it. And now this will get deprotonated as well. So initially at the end of the first reaction, this is the product of what we will have right here, because that hydrogen will be deprotonated. So therefore, when we do this water workup step, now we'll be able to convert this into our neutral alkyne. And another reaction. So here's reaction number 7. We have a dihalide, and in this case right here, this will be the vicinal dihalide because the two leaving group are on a different carbon. So in this case right here, we'll be able to pick up one of this hydrogen and one of this hydrogen. So this hydrogen right here, E beta with respect to this leaving group. And this hydrogen here, E beta with respect to this leaving group. So in the end, we'll be able to form a triple bond between these two carbon-carbon bond. So the product of this reaction would then be as follows. And you can see we form a very similar product up compared to what we have above. So initially this is deprotonated, but followed by the water workup step, then we'll be able to make this product right here. So these two halide right here, our two dihalide produce a very similar products. And now reaction number 8. So let's say here we have this dihalide, and again this is a vicinal dihalide right here, so the two halide are on a different carbon. So we first take this and react this with sodium amine, and follow we are now adding another alkyl halide to it. So what will be the product? So in this case right here, there's no water workup step, but the step that will be followed would then be the addition of another alkyl halide. So initially, the product of the first reaction would then be as follows. Again, we'll be able to form the triple bond along the two carbon-carbon bond. And in this case right here, it will be producing a terminal alkyne, right? So because the triple bond right here, and this is on the terminal end. So therefore, it would then be deprotonated. So the product of this reaction initially would then be as follows. Oops, and we miss out on one of the carbon. So oops, that seemed to be correct. And now this E become deprotonated right there with the sodium. So that will be the product of the first reaction right there. And when we now take this and react this with this with another alkyl halide, then this carbon right here is nucleophilic and be able to come in and attack this carbon right here, kick off this leaving group. So in the end, the product then be as follows. So we would, because please try to correct this bond angle whenever we can, because we know that this carbon right here sp2, so a bond angle would be 180 degree. So please correct that to make sure it's straight whenever we see the alkyne. And so it is not a major point, but we just want to make sure that we get the bond angle correct whenever we can. So there you go. So that will be the product of this reaction right here.